You should have picked up this warm-up when you walked in. And it can be a little bit confusing because you don't have the mass or the velocity. Okay, so, but you know that the overall momentum is 24. So we have to kind of look at it like this, that the momentum's 24, which is equal to that mass times the velocity. And both the m and the v are unknown, but we know that multiplied together they equal 24. Okay, so A says if it had twice the mass and moving at the same speed, which means these are multiplied together, so I would multiply that mass times 2. The velocity stays the same. So I'm multiplying this side by 2. I need to multiply this side by what? By 2. 24 times 2 should be 48. You're going to see that it actually times 2 is the same because mass and velocity have the same impact on the momentum. They both count equally. C says 1/2 the mass was moving with twice the speed. So I kind of run out of room, so I'm going to write it down here. We have 24 is equal to... So I don't like fractions because I'm an adult. I don't have to use them. So I use 0.5. And 0.5 times 2 is 1. So C is just 24.
Will you have these questions on a test?
I have no idea. If you want me to be honest, I haven't looked at the test lately. Same mass and moving with half the speed. So again, this side is going to be just times 0.5. So I have to multiply that side times 0.5. 0.5 times 24 is 12. And I know I'm not putting the units on here, but it gets really messy with my big handwriting and the units. All right, E says 3 times the mass and half the speed. So it'd be 3 times the mass and half the speed. So I have to multiply this side by 3 times 0.5. And when you do that, what do you get?
When you divide it by 36.
36. I don't like fractions because I don't like to have to flip them. So I just use decimals instead when I can. So 36. And then F says 3 times the mass and twice the speed. That's going to be 3 times 2 is 6. So 24 times 6 should be 144. Okay, so a little bit of math involved, but this is more of a thought question than a math question. Any problems with this so far? All right, today is the last day for a new formula.
Yay!
Until after the test. Until after spring break, actually. No new formulas. It's actually easier. So your test, just so you know, right now is planned for March 10th. So that means next week, I know we have the SAT coming up and stuff, so next week it's just going to be studying and practice and practice and practice and practice and practice. And the following week we get to test right before spring break. All right, conservation of momentum. In a closed system, which means we're leaving out anything on the outside. We're not even going to deal with friction and on level of physics. So just what you're looking at, only those things. So in a closed system, we're not adding any mass after the collision or taking away anything. We're not subtracting the pieces of the car that fell off, like the tire when it goes rolling by, any of that. So in a closed system, the change of momentum is 0. Okay, and remember, we do that delta P where that triangle means change in. P, lowercase p is momentum, so delta P is 0. You should have seen this yesterday in that lab we did with the carts. The change in momentum was always 0 with a little bit of rounding.
Yeah. Or like really close.
It should have been like, yeah, it was a rounding issue. So this also means that the momentum before a collision is equal to the momentum after a collision. So this week we talked about apart collisions. That is where you have two separate things that collide and then they go, however they're going to go afterwards, on their own. They are not attached. Today we're going to talk about when they're stuck together. So the important thing with dealing with collisions is collisions are basically what we call a DIY equation. It means you build it yourself. And the most important thing to do when you're looking at collisions, the first step, label your before and after types.
I thought DIY means do it yourself.
That's what I said. Yeah, do it.
Oh, I thought you said do it.
Do it yourself, which is like build your equation yourself.
So DIY.
All right. So for our examples today that we're working through, I put pictures. Know that there's not always going to be pictures. We have a 1,000-kilogram train traveling at 5 meters per second east. Let's review our directions here. Never, ever, and then whatever you're taught. You have north, east, south, and west. Just as a refresher, we consider both north and east to be in the positive direction and west or south to be negative. That's why we say to the right is positive, to the left is negative. So in this case, it's giving us east, so it's going to be a positive velocity. It strikes and clamps onto a 1,500-kilogram train car going 1 meter per second east. Okay, these are going in the same direction. This guy's just slower. Doesn't get hit from behind. What type of collision is this? Are they together right now? No. We're going to label that then as an apart. Okay, it says when they hit, they clamp together. Are they still apart? No. They're together. Okay. It's almost lunchtime, and I realized y'all are all hungry. I get it. I'm hungry too. If for lunch I have a bologna sandwich, I do not. I really want one because I've been talking about it all day now. But let's say we did. And I eat that bologna sandwich, and then the bell rings, and I go off to my 5th period class. That bologna sandwich is now part of me. It is coming with me until my body breaks it down and I leave it behind in after-school activities that we're not going to talk about. So when something is together, their velocities are the same. Okay, me and my bologna sandwich, we're gonna go together at whatever speed I happen to be walking at. From lunch to fifth period is usually pretty slow. I've seen y'all leave the lunchroom. That y'all aren't speeding. If we're linked hands, same thing. If y'all like to hold hands sometimes when you're allowed to, and for some reason that slows down your velocity, because y'all walk slower, and then people have to walk around you. But whatever speed y'all are walking, it's together. One of you's not walking 3 and the other one's walking 0.5. You wouldn't be able to stay together. So I have my collision labeled. I'm going to do my little squiggly line, just what we've been doing. Because this is a part, I'm using my apart formula, which is M1 times V1 plus M2 times V2. I'm going to just go ahead and solve for this side of the equation. After you plug everything in and solve through, you should get 6,500. Now, conservation of momentum, which we talked about up here, says that before equals after, so I can put my equal sign here. Then I've got to solve for my after. So in this case, their masses get to be added together. We have our formula right here. M1 plus M2 times their velocity together. Because now their mass is the whole thing.
You just add the velocity?
That's the multiply. So it'd be 1,000 plus 1,500 times V. Okay, order of operations says you got to make sure you do that parentheses first. And I'm left with that. I cannot combine those or do anything else. I'm left with 2,500 times velocity for after. But I want to know what that velocity is. But keep in mind, these are equal. So I'm going to move my equation up here. What can I do to get V by itself? Divide. East. Because I have the direction, so I might as well include it. Any questions about that? For me personally, the together aspect of collisions is a lot quicker to solve and a lot easier. All right, now we have a 2 kilogram fish swimming at 3 meters per second, eats a 0.5 kilogram fish swimming at 1 meters per second in the opposite direction. So what does that mean for the velocity if it's in the opposite direction? It's going to be negative. So I have 2 separate fish, so I went ahead and labeled them apart. M1 is 2. V1 is 3. M2 is 0.5. V2 is negative 1. My equation for a part, M1, V1, M2, V2. A little squiggly line, that's a very sad squiggly line, but it's fine. Then solve for my momentum before. I got a momentum before the collision of 5.5. So what y'all got? Okay. So after, now the little fish is inside the big fish. So they're together. So I've got to do M1 plus M2 times velocity. 2 plus 0.5 V. 2.5 V. Okay, since before is always going to equal after, I can set those equal to each other, and my equation is like that, which I'm going to rewrite over here. 5.5 equals 2.5 V. Divide both sides by 2.5, and that's going to give you a velocity of what? 2.2 meters per second. What is the most important thing to remember when doing collisions at this point? Make sure you make it negative when it's velocity, and make sure you're using the right equation.
Would it be considered going east according to the picture?
You could. Yeah, you can put east or right. Because it doesn't have that direction, I don't feel inclined to put it. It's just, I kept my velocity of the big fish positive. If you had set the little fish's velocity to negative, you would, positive, you'd have a negative velocity, and you just have to kind of keep that straight. Okay, look at our this one. All right, before my collision, what type? Is this together or apart?
Apart.
This is apart. Is this together or apart? I know.
It was hanging up in the jacket closet.
We'll take a picture later.
It's
She lost a very expensive jacket. So.
Oh, I just did that whole thing.
Uh-huh. So the mass of 1 is 0.75, and it's traveling at 2. Meets and sticks with a 0.48 clay blob traveling at 4 in the opposite direction. So since this is apart, What is my momentum before the collision? Negative 0.42. Since this one is together, m1 plus m2 times velocity. Since those are equal, you set them equal to one another, and I got 1.23 times v. That is my equation I'm working with, so I'm going to divide both sides by 1.23. Now, I grade your tests. I know that this is where you mess up, because we all like to divide big divided by little. It just gives us better numbers. In this case, we have to divide that 1.23 by both sides to get v by itself. So make sure you're not rushing through this and making a mistake that you know better just because we're used to dividing big by little. It's going to give us a velocity of what?
Negative 0.33.
I had negative 0.3.
Same thing. Rounded.
What did you say? Oh.
So negative 0.3 meters per second. So when these blobs collided, they kind of shifted a little bit backwards before they stopped, because negative 0.3 is not a very big velocity. Are we seeing this pattern here? All right. I was super proud of this next one because I made it up, and then of course I messed something up. So my deer is going to be swimming at negative 2.
So we're gonna have to.
No, we could if you wanted to, but we don't have to. So, but you're not going to give me the credit I deserve for this one. But that little alligator is smiling and his hands are on his belly because he ate. So a 452 kilogram alligator speeds up to 6 as he sees a 68 kilogram deer swimming at negative 2 across the water towards him. What is their velocity after the collision? So before the collision, they are apart, and after, they are bonded together, much to the deer's dismay. Now, I know that this is not an actual situation. I realize that the deer would take down, or the alligator would take down the deer, drown it, and then do those rolls to break off chunks of the deer. Like, I realize all of this. But this is make-believe, kind of. This is physics, so we're not going to take it. We're just going to assume that the alligator is so big that you can just swallow that up. With 2,712 plus negative 136, and so when you add those together, you should get 2,576 for the before. That's going to equal my after. My afters together, m1 plus m2 times the velocity. That's a plus. That's not a time, sorry. Plus. Should get 520 times v. From there, what do you do? Divide by 520 to get v by itself. Yep. Don't be rushing. We have nowhere better to go. And the alligator keeps swimming at 4.95 meters per second. We're going to continue to practice this. Does anyone have any questions? So watch your velocities and watch your types. Those are the two most common, and make sure you're not rushing through math and dividing by the wrong thing. But those are the two most commonly seen mistakes on these. So we're going to do a lab interactive. It looks not like that. It looks like this. All right. On the sheet of paper that you picked up from me, there's a data table. You click through these in whichever order makes sense to you. I'm not going to tell you how to live your life. Personally, I went 1545, 1560, 1575, then 20, because that helped me see the pattern. Okay, so I'm going to click on this guy. Whoop, and he eats. So before the collision, my big fish weighed 45 grams, and he's at rest in all the collisions. And my little fish weighed 15 and 80. There are spots for you on that lab to fill in with that information. So you put the little fat fish, mass in grams, big fish. There's no spot for the big fish's initial speed because it's always 0 in this online lab. So it just wants the little fish. Then it's going to ask for the final speed of both fish. Why doesn't it separate them? They're together.
So you would just add them, right?
You don't even have to do that. It does it for you. They're together. So each of their velocities, because technically the little fish is inside the big fish. I mean, slowly being digested, melted, probably alive. But they're both going 20. So their final velocity is 20. Because that little fish, if you're in a train that goes 60, you're speeding across the country going 60. So that little fish is being digested and traveling at 20 centimeters per second. So there is no math on this worksheet. Everything is given to you. Now, if you see these numbers being replaced by hashtags, those are actually what we call number signs before Twitter. And all you have to do is return the options and rerun it, and it'll generate it. Yeah, before Twitter. Sometimes you don't see, maybe it's dark. We're not here to judge his actions. And it could be dark, and lots of fish have high camouflage, and maybe you don't see them. I feel like you're being a little judgy, okay? I'm not here to judge your actions. Don't judge the actions of the fish. Once you've collected all your data, you're going to answer these in, complete sentences because we're almost adults, so you can write me one sentence. If you're not seeing that pattern of with the small fish and the big fish, I need you to think back to those golden days of elementary school where you got to sit on the little scooter things on the floor and you could roll around the gym. Yeah, those were great. So imagine that you now goes back to that gym and sits on one of those, and a kindergartner is so happy to see you, and they run up and jump on you. What's going to happen to your velocity as you go backwards? Is it going to be a fast velocity? Is it going to be slow? You got to think of it like that. What would happen if, instead of you sitting on the little scooter, it was me with a larger mass? What's the impact going to be on my velocity backwards? And then you can also think of, what if it's not a kindergartner, but a 5th grader that's super excited to see you with a much bigger velocity? What's going to happen to your velocity going backwards? You got to think of this in terms of momentum. Because remember, that momentum before is equal to that momentum after. Does anyone have any questions on my expectations on this? Cool. Get started.